In a standard vector space, the rules of engagement are strictly limited. You can add two vectors together to get a new vector, and you can scale a vector by multiplying it by a number. But you cannot multiply a vector by another vector. The mathematical structure simply doesn't allow it. This restriction raises a structural question. What mathematical behaviors emerge when we force vectors to multiply with one another? The solution is a framework known as a linear algebra over a field. It is a system of rules that unifies matrices, linear operators, and polynomials under a single mathematical architecture. To see how this works, we will define exactly what an algebra is, construct an infinite sequence space from scratch, and rigorously define polynomials without ever relying on the ambiguous concept of an unknown variable. Moving beyond basic vector spaces to linear algebras provides the exact mathematical machinery required to decode advanced linear transformations. We define a linear algebra over a field F as a standard vector space equipped with one additional specific operation, vector multiplication. This diagram lists the three non-negotiable axioms for this new vector product. First, it must be associative. Second, it must distribute over addition. And third, it must be compatible with scalar multiplication, meaning scaling the product of two vectors is identical to scaling either vector before multiplying them. An algebra might also possess two special conditions. If the order of multiplication doesn't change the result, the algebra is commutative. If there is an element that leaves any vector unchanged when multiplied against it, the algebra has an identity element. Consider the set of n by n matrices over our field F. This set satisfies all the axioms of an algebra and possesses an identity element, the identity matrix. But if n is greater than or equal to 2, matrix multiplication is absolutely not commutative. Next, consider the space of linear operators on a vector space V. If we define our multiplication product as the composition of two operators, this space also forms an algebra with an identity element. Matrices are arrays of numbers, while operators are mapping functions, yet both obey the exact same algebraic axioms. Because they share this identical architecture, any theorem proven for the abstract algebra applies equally and automatically to both matrices and linear operators. When we first encounter polynomials, we are taught to use an unknown variable, x. This definition is mathematically circular and imprecise. To build a rigorous framework, we must establish a structure where x is a specific known object. This array represents the vector space F infinity, defined as the set of all infinite sequences of scalars drawn from our field. Within this space, vector addition and scalar multiplication operate purely term by term. You add the first term to the first term, the second to the second, and so on. The formal multiplication rule for F infinity is calculated using convolution. To find the nth term of a product, you iterate through the sequences, summing the products of terms whose indices add up to n. The identity vector for this specific algebra is the sequence beginning with a 1, followed by an infinite string of zeros. We define x as the specific sequence where the scalar 1 occupies the second position, followed by infinite zeros. Let's apply our convolution rule to multiply x by itself. Computing x squared simply shifts the 1 one position further down the sequence. By extension, computing x to the power of k shifts the 1 exactly k positions down the line. By defining x as a physical shift operator within an infinite sequence, we replace the ambiguous variable with a concrete mathematical object. From the infinite expanse of F infinity, we isolate a specific subspace called f of x. This subspace contains only the finite linear combinations of x and its powers. This visual equation shows how a formal polynomial maps perfectly to our infinite sequence model. Because the linear combinations are finite, the sequence eventually hits its highest power and terminates in an endless string of zeros. Because f of x is a subspace, it inherits all the algebra rules we just established in F infinity, the term-by-term addition, the scaling, and the convolution multiplication. The degree of the polynomial is the integer n tied to the highest non-zero term. If the scalar coefficient of that final term is exactly 1, it is defined as a monic polynomial. Every polynomial exists as a static, finite vector residing within the strictly defined algebraic subspace. This brings us to Theorem 1, which governs the product of two non-zero polynomials, f and g. This formula dictates that the product of f and g is always non-zero, and the degree of the new polynomial is exactly the sum of the degrees of f and g. The proof relies on the fact that our coefficients are drawn from a field. The product of two non-zero scalars cannot equal 0. Therefore, the highest degree terms in our polynomials can never cancel each other out during multiplication. The theorem also details that multiplying two monic polynomials always yields a monic polynomial, and that the degree of a sum of two polynomials will be, at most, the maximum degree of the individual polynomials. These results define f of x as a commutative linear algebra with identity. Theorem 1 guarantees that we can safely manipulate polynomials. Specifically, if the product fg equals fh, the absolute lack of zero divisors ensures we can safely cancel f to prove that g equals h. Because polynomials, matrices, and linear operators are all algebras over the exact same field, we can take a polynomial and evaluate it using elements from any of those other algebras. This grid presents a simple base polynomial over the complex numbers. F equals x squared plus 2 times the identity. We can evaluate this polynomial using a standard complex scalar, such as 1 plus I. Expanding and reducing the equation yields 2i plus 2. We can evaluate the exact same polynomial using a 2x2 matrix B. The result is that matrix squared plus the scaled identity matrix. And we can evaluate it using a linear operator T, giving us the composition of T with itself plus 2 times the identity operator. Theorem 2 proves that evaluating polynomials perfectly preserves algebraic operations. Adding or multiplying polynomials before evaluating them yields the exact same result as evaluating them first and then performing the arithmetic. Polynomials act as universal evaluators. Operating purely on foundational algebra axioms, we map abstract polynomials onto concrete matrices and operators without breaking the mathematics. By stepping back from the abstract mechanics, the theoretical payoff becomes clear. An algebra is simply a standard vector space upgraded with strict rules for vector multiplication. A polynomial represents a precise, finite vector residing inside an infinite sequence space. That shared algebraic structure is exactly what allows us to evaluate those polynomials using matrices and operators seamlessly. Mastery of linear algebra depends on recognizing the axiomatic architecture that connects these seemingly different mathematical objects.